Hello, my name is Timothy Hanneman, and I will be taking you on a brief tour of some of the ongoing research that we are working on. I'll be covering 5 sections: a brief introduction to what software-defined networking is, what the research problem is, some of the tools and methods that we are using to investigate, and where we plan to go with the research. Software-defined networking is a recent networking technology that approaches the creation of networks differently than traditional networks in the past. In software-defined networking, the data plane and control plane are separated. What this means is that the functions to control decision-making and the process of matching decisions to forward network traffic are separated. This image here might make things a bit more clear. On the left, each of the colored cylinders represent one device that moves data across a network. In the software-defined networking architecture, the control function is separated from being on each device, and another device takes care of that for the network. It is called a controller. The apps in this image are applications that interact with these network devices, not quite like the ones you might use on a smartphone. The design of a network and where devices are placed within it affect network performance. Where on a network that a controller is placed will also impact network performance, and because of its importance, its placement has an impact on the performance across the entire network. For example, the image shows two controllers connected to the left-hand side of this network. This may not be ideal for devices on the right. The research focuses in on trying to find an optimal placement. There are several aspects that are affected by the placement of a controller within a network. This includes the control latency, resilience, reliability, load, cost efficiency, or a combination. Control latency is the delay that happens when part of a network communicates with a controller to learn how to forward network traffic. Resilience, a characteristic of being able to continue operation even with some network failures. Reliability is measured as a percent of uptime, or the time for which a network service can be accessed. Load balancing, where network traffic is distributed, or it is shared so as not to overwhelm any particular service. Cost efficiency is implementing services in such a way as to minimize costs, such as buying more equipment than is needed. Multi-objective is where analysis is done to find good compromises between these subject areas. We'll now be moving on to the methods section. There are 3 main components that are being used: Mininet, Oracle, VirtualBox, and Python. Mininet is an emulator. It allows the construction of virtual networks to simulate information going over a real network. It also gives the ability to run tests over multiple network topologies. VirtualBox is software that allows for the virtualization. We run Mininet and controller software from it. Python is a programming language that is used to generate different networks from Mininet and test them. Here's an example of a bandwidth test running over a network. Each window that you see here represents a simulated host. This here is a small snippet from another bandwidth test. This time, it is running tests over a linear network. Each time the test is run, the number of switches in the network is increased. We can observe the impact that the size of the network has on decreasing bandwidth. This is all very exciting, but we aren't quite done yet. Up next, we'll be designing more specific test cases and measuring the results. In case you're curious, here's a timeline of the process. If you're interested in software-defined networks, take a look at the links. Thank you for listening.